Good evening. As requested, I will be giving a talk about Lisp tonight, and I will be doing it from a personal perspective, how I got mixed up with Lisp and its consequences, I guess. So you can expect some personally oriented information tonight. So firstly, Lisp, what's it all about? Well, it's actually a list processing language, but from the point of view of a number of critics, you'll find that the LISP is often referred to as lots of infuriating, silly parentheses, but that can be fully justified, as you'll find out later. As I said, this is a thing in context. So firstly, where does Lisp fit into the programming language history? Well, from the UK point of view, Autocode was the first high-level programming language, and it was a family of languages developed at Manchester University in Cambridge and London in the 1950s, and it was originated with the Manchester Mark I computer in 1952, and I tie myself back that far by at least to 1965, where I did some programming on the Atlas computer using Atlas Autocode. Now, where does Autocode fit within programming languages? Well, just a couple of comments here that it was related to Argyle 60, but didn't have quite the same context, same contents. But a couple of the interesting things about it was it had arrays which would be dynamic in the sense that you could determine the actual size of the array during execution, which was unique at the time. It was also the first high-level programming language which actually had a complex data type, mainly from the needs of the electrical engineering department at Manchester. So it was a fairly sophisticated programming language. It also could directly include routines at the machine code level to get improved efficiency. So Autocode was pretty important. If you, however, are looking at this from an American point of view, then Fortran will be claimed to be the first high-level language, basically from 1957, which is about 4 or 5 years after Autocode. And then Lisp came along in 1960. And 1960 is way back. It was originally developed in 58 by John McCarthy, but became known, if you like, in 1960 and is still in use. And if you were to look around, you'd see there are a number of current variants available. Common Lisp, Scheme, which was from MIT, Racket, and Clojure. So let's give ourselves a little bit of background to Lisp here. If we want to take an arithmetic expression, there are 3 notations to represent that expression, which we can use. There is infix, and what you would expect is that the operator, in this case, the function being performed is placed between the variables which are being computed. So B plus C, you get the plus in between here. That's the conventional environment. Second one is postfix. This is where the actual operator appears at the end. The most well-known language in which this was used is Forth, and it doesn't need any parentheses, in fact. So you would have the value B, you'd take the value C, and then you would add them together to produce the result. So no parentheses. Finally, there's prefix, in which the operator is at the beginning. So in this case, we have plus B and C. Now, that potentially has lots of parentheses, because do you know where the end of the function is? Possibly not. So therefore, in Lisp, the plus could be replaced by any function, and the whole expression became a list. It was all put in a bracket, so you knew how far that operation was to be performed. So why lists? Well, it's basically Lisp's major data structures, or one of its major structures, and it really created a complete new syntax for representation of information and the programs. So the source code is also as a list, giving the possibility that you can have your program manipulate your source code. This interchangeability of code and data gives Lisp its differentiation, if you like, from others. Generally, a program is referred to as a set of S expressions or parenthesized lists. And in general, any statement within Lisp will be of the form of, as shown there, if you had a function f, it takes 3 arguments, then it would be brackets f, arg1, arg2, arg3, closing bracket. So that is a list, and it is also a representation of a program within the Lisp context. So from a formal viewpoint, where did Lisp come from? Well, when proposing programming languages, we go back as far as Alonzo Church's lambda calculus, which was the way in which you could represent an expression which could be computed using a Turing machine. And essentially, Lisp was the notation used in order to represent a lambda calculus. And so it quickly became a favorite programming language, particularly for artificial intelligence research. And as one of the earliest programming languages, it included many things which we now think of as standard, if you like. Tree data structures, storage management, dynamic typing, high order functions, recursion. All of these things are considered quite normal within a programming language these days. So where do I come into this? Well, a gentleman by the name of Robin Jones, who was a university colleague of mine, the University of Canterbury, together with Ian Stewart, who I consider to be a fairly famous mathematician, he's now emeritus professor at Warwick University in the UK. They wrote a book which was called Peek, Poke, Python, Ram. And it was essentially basic programming for the ZX81, which was a small personal computer, one of the earliest. And it was actually quite successful and written for a British publisher. Later, they were asked to go to a different language, and they then wrote The Art of C Programming in 1987, the two of them. And they wrote it for Springer Verlag, a German publisher, essentially with the aim at selling into the American market. And it was quite successful. So they were well established at this point. And then along came myself. I was asked to join them. And we wrote a book called The Art of Lisp Programming. So that's where I get my first involvement seriously with Lisp. Now, Robin and Ian are shown here, but Ian is not only known as a mathematician, he is also known for having worked with Terry Pratchett, the author, and involved in books called The Science of Discworld, etc., a whole series of books on that. So Ian has both serious mathematics and, if you like, enjoyable books as well. And so the three of us got together to write this book. And when I say we got together, we worked ourselves together remotely. And in fact, in all the work we've done together, I've never actually met Ian. We've only been in remote contact. Now, let's have a little bit more on the book. Well, we actually obtained permission to use the illustrations from Alice's Wonderland Adventures in Wonderland and Through the Looking Glass, and also the rights to quote from the books. And that was really good. It helped the structure of our book, and it made it more enjoyable for the reader. So, for instance, a quote there, what does it live on, Alice asked with great curiosity. Sap and sawdust, said the gnat. Go on with the list. And that was from Lewis Carroll, Through the Looking Glass. It's amazing how many good quotes and cartoons are useful from within those books. So here's one of the cartoons. The white rabbit put on his spectacles. Where shall I begin, please, your majesty, he asked. Begin at the beginning, the king said very gravely, and go on till you come to the end. Then stop. That's from Alice's Adventures. And so we will begin at the beginning. Let's start our journey into Lisp, considering how we might represent text as a list. There are all sorts of formats you could use here, and this is a simple but not very efficient one. For instance, we had a sentence here to represent with the cat sat on the mat, and a block of memory is allocated to each of the words. The amount of memory allocated was not, in this case, dependent on the size of the word, though most of the words are only 3 letters anyway. But it is a way of representing textual information, but it's not very efficient. So what if, for instance, we wanted to add a new word, so it became the black cat sat on the mat? It would mean that we'd have to move our array of words in memory, which is not very efficient. So can we represent text as a list in a more efficient manner? Well, looking at the top here, we now have each word separate, but with a pointer to the next word in the sentence. So the is followed by a pointer which points to the second word, which is cat, with a pointer pointing to sat, etc., on through the whole sentence, and finishing with a nil pointer. Now, is this any better? Well, if we look at the picture at the bottom, the figure at the bottom, you'll see that if we now want to put in our extra word black, we simply have to change the pointer from the to the word black, and from the end of the back to the cat, and without moving anything around, just by changing those pointers, we are able to add that extra word into our string. We can take this even further. We can make pointers a much more serious part of our structure. So this is even better from the internal representation point of view, but not necessarily from your point of view visually. So everything is in pairs of pointers, and each of those pointers can point to other structures of the same general type, or to terminating symbols. So for instance, if we see the left-hand pointer, which is pointing down in this diagram, it's pointing down to a set of 3 sets of pointers. One goes on to firstly goes on to T as a symbol, then the next one goes on to H, then the next one goes on to E, and then there's a nil. So that's the word "the" is represented by that piece of the string. The right-hand pointer at the top points on to the second such string combination, where the left pointer goes down to the word cat, and the right one goes on to the rest of the structure. So generally, only left pointers can point to terminating symbols, and only right pointers can be nil. And where we do get terminating symbols, such as letters, we generally refer to them as atoms within this context. Now, that's starting to look a little bit complicated, and it's not in a form, of course, which we can start writing programs with. So we need to change the information. We need to change from our diagrammatic notation to a symbolic notation, which will allow us to represent and manipulate the information within our strings. So for instance, if we had a list of letters A, B, C, D, it becomes written in our symbolic notation as in brackets A, B, C, D, closing bracket. So for instance, for our original sentence, it would be, and reading out makes it very difficult, as you can see the infuriating silly parentheses bit. If we say bracket, bracket, the, closing bracket, open bracket, cat, closing bracket, open bracket, sat, closing bracket, open bracket, on, etc. So we can visually see it. We can see how our parts are defined. And of course, we can relate this back, if you wish, back to the diagrammatic representation which we had before. Generally, consider that spaces were used to separate atoms, but otherwise were considered to be insignificant. If you take your computer and just open a Lisp interpreter on it, we can very simply see how some things work. So for instance, if we just have an opening and closing bracket and hit return at the end there, it'll just come back and say nil. There's nothing in there. We don't have anything in our list. But if we did the bracket plus 3, 7 closing brackets and hit return, we get the answer 10. So we can see there that we're actually getting an operation done and a result is being returned. The result of the computation is being returned in this context. So what if we try to add more than 2 values? So here we're saying brackets plus 3, 5, 2, 5, 3. What would one expect the Lisp processor to do? Considering another possibility, what if I wanted to decrement a number? So I decided there should be a function dec, which if we say dec 6, would it work? Would it give me an answer of 5? Well, here we can see if we do our plus 35253 operation, we hit return, we'll get our value 18. So what it says is that the plus function can take a number of arguments and it simply adds them all up. On the other hand, if we haven't really defined our dec function, it's not part of the core functions available, it will just come back and say it's an undefined symbol dec, and well, it's up to you to now make some definition of this. So the first thing we can say then, there are obviously functions that exist and also some that don't. So the important question then is, how do we create new functions? Well, the word for doing this, the function, if you like, to make functions was called defun. But within the variations of Lisp became define, and so in general now we consider the function define, and it has arguments. The first argument is the name of the function which you're defining, and the second is the list of its arguments, and then a list which represents the action which the function is to take. So putting it into the context of our definition, we can say here we're defining the dec function. So dec takes on an argument x, and what we expect to happen when we say dec of x is that we take minus x1, which is in brackets there. So it's taking the value of x, taking 1 away from it, and returning whatever value you get. So we can now define a new function. Notice this formatting which I've done here makes it easy to read, but it is not imposed within the language. That is not a compulsory part of the representation. So we now know what a list is, but how can we decompose it into its component parts? Well, what we need to do is to think of what are the basic component parts of a list. There's the first part of the list, and you can consider the rest. So we have basically what we were calling the head and the tail. So we can have a function head which removes the first part of the list. We can have a function tail which returns the rest of the list. So if we had a list, bracket A, B, closing bracket, open bracket, C, D, E, closing brackets, we can consider that the list A, B in brackets is the head of the list, and C, D, E is the tail. For your own thoughts, what do you think of the head of a list? What would that be in this context? In the original Lisp, these operations were actually called car and catter, which were actually directly derived from the IBM 709 instruction set, which split an address into 2 parts, which is just what we needed for using our pointers. So firstly, then, there are no assignment statements in Lisp. There are only functions. So if you want something to take a value, we need a function to do that. This is called setQuote. And I say for very specific reasons, we're not going into the depth here. But the symbol x in this context, if we say set quote x1, is we take the symbol x and we allocate the value 1 to it. So when this is executed, it also returns the value, which in this case is the 1. If we executed set q yx, it assigns the value of x to y, which in this case is 1 from our previous definition. What if, on the other hand, we want y to have the value x, in other words, the symbol x? So we need another function which forces that process, and we call that function quote. And what quote does, returns its own argument. So we can now say if we want y to actually be defined as being the symbol x, then we can say bracket set q y, then quote x. Now writing that out is a little bit, I don't know, takes too much work, unwieldy. So there's a shorthand version of this where we just use a quote mark in front of the argument there. So we have set quote y, quote x, and it's written with the inverted comma. So where are we getting to? We can now take a list apart, but how do we assemble one? This is the opposite process, and function in this case is called cons. So for example, if we had set quote h is a, and set quote ta is bcd, I should have said quote bcd, then the cons of h and ta simply produces the list abcd. So we can take things apart, we can put them back together again. What surprises a lot of people when they start looking at Lisp is that with these and only these functions, we can do anything we like with lists. It's a very surprising thing. We don't need a lot of complexity. The other functions we have for manipulating lists are simply icing on the cake, extra functionality. Now, what I've done now is given you the entry point into Lisp, but I'm not going to go much further in this case. So as I said here, I don't wish to overstay my welcome with this, so I will finish with just 3 more slides. And go on until you come to the end, then stop. So, we've been talking about Lisp. Is it something which is worth looking at? So, is it a dead language? Probably the best way of measuring that in a sense is, can people earn money programming in it? If we look at the top paying technologies, programming technologies of 2022, and see the results, we'll see that Clojure gets the highest pay. Other languages run down there. The fourth one down is Lisp at 95,000. And we get down to Perl at 90,000. Where, you might ask, is Python? Python's down here at about 71,000. Now, of course, any surveys can be manipulated to represent what you want. So whilst I'm saying here that you're getting high pay for Clojure and Lisp and even Perl, it's not saying how many people are employed at these levels. Yes, so there are still people using it and they earn money, okay, do well. That doesn't mean to say that there's that they are in any sense significant numbers. So yes, it's still a valid language, and if you're good at it, you can do quite well out of it. But the numbers are not quite as high as they used to be. Is that all? Alice timidly asked. That's all, said Humpty Dumpty. Goodbye. And that's the end of this story.